Miguel, I want to make a short introduction. After that, we can start. Miguel?
Yes, please. Please go ahead.
Okay.
Sorry.
Merhabalar, hepiniz hoş geldiniz. Ben bugün bildiğiniz gibi nZEB, yani yaklaşık sıfır enerjili binalar kısmını eğitimini Sayın Miguel Feliz yapacak. Bağlantıyla alakalı zaten en alt kısımda interpretation var. Hani oradan ikinci kanalı, yani Türkçe olan kanalı seçerseniz eş zamanlı tercüme de gerçekleştirilecek zaten. Yavaştan başlayabiliriz. Miguel, you can start. Thank you.
Okay. Thank you all. My name, like you just heard, is Miguel Feliz. Feliz means happy in Portuguese. So let's hope that this would be a very good session, a happy one, and we all could learn a little bit more about net zero or near zero or no energy buildings. I will try to keep it short. I know it's after lunch in Turkey. It's before lunch in Lisbon, where I am right now. We are going to try to speak a little bit about all aspects of the net zero buildings, starting with why the necessity of having net zero buildings. Then speak a little bit about the approach, especially in the European Union regarding the net zero. Then a quick break for some coffee, and then a more physical aspect of this, to state what is the approach in our project for the net zero, and finishing with a small example of how a real world building can be turned into a net zero building, with all the difficulties, with all the shortcomings, but also with the easiness of making a good audit and implement the measures that are necessary to accomplish the definition of net zero. Afterwards, like always, we have some question and answers. But please feel free to interrupt me if you have any question, or if afterwards you have another issue or another question or something, please drop me an email or something, or a text message or wherever, which we will reply back soon. And we are really happy to help to understand everything around this subject. So why net zero energy buildings? Let's start with the obvious. This is a chart. I didn't translate the chart. I didn't did anything on the chart. I just copied here for you to know the importance of the consumption in buildings. This represents around 30% of the world energy consumption, the world total energy consumption. And as you can see, it is pretty much stationary in the developed countries, but it will grow a lot in the non-developed countries. So this is an issue right now, but it will be really a big issue in the future, especially if you want to carry on with emissions reduction targets that everyone talks about. Every country has the buildings in their wish list for energy outlooks. Turkey has a plan. That's why we are here. Portugal has a plan. Everyone wants to keep the building sector in check regarding the energy consumption, especially in the future. And the trend is really clear. So it's 20-30% of the total energy use, depending on the source that you use, but it's 30 to 40% of the carbon emissions. It will grow, and all the reduction targets will require that the buildings reduce the consumption, or at least keep it steady in the next future. So net zero buildings will help to slow this trend, and that's why they keep up popping in all the conversations regarding buildings and regarding the energy. So firstly, this is important to set the conversation. What is the N in the nZEB sentence? So it's net, it's nearly, it depends a lot on the source that you use, the country you are into, or the idea that you want to represent. For example, in the United States, it's the zero energy building. So the building must be completely with a zero balance between the outside grid and the energy consumption. The Green Building Council, it's slightly different. They only say that the building is highly energy efficient and is fully powered from on-site or off-site renewable energy sources. And in the European Union, the concerted action of the APBD, which is the directive of energy efficiency in buildings, they say that 40% of member states don't have yet a definition. So what I'm trying to say here is that the definition of net zero or near zero in buildings is a fluid definition. So what we're trying to say is that they must be efficient. And there's always a role for renewables to offset the consumption that the buildings have. And then there's always a question: are we talking about final energy, primary energy, or emissions? And it's possible to find one definition for all geographies and for all the entities that relates to this. This is important because the near zero, net zero, above all, is an idea, is a concept that can relate to the reality, to real world buildings in several ways. This is some might say that this is a rich world problem, so it's a developed world problem, because the consumption in buildings normally comes from air conditioning, the lightning charge, people. So it's mainly higher income problem. Right now, it's true. The overall energy consumption, like we saw in the first graph, it's higher in the developed countries. And the per capita, so the square feet, square meter energy is also higher. But the situation will evolve because, as you saw in the first graph, the increase in consumption, it's growing a lot more in the underdeveloped countries. So this will be a global problem, and the consumption in buildings will grow everywhere, not just in the developed countries. And the new buildings, which are much easier to take care because they are made from scratch, they are now and will be a fraction of the building stock. So if we want to take care of something in the building sector, we have to move and take care of the existing building stock. So it's very difficult to change this in the foreseeable future, and it will be a huge effort to take care of old buildings. So there's a lot of residential buildings built before 1970s, when the first regulation regarding energy efficiency came up in the European Union. A lot of small fraction, 5% of the residential buildings were built after 2010. So it's really important to know that the old buildings will be very important to set up these objectives that everyone is talking about. This is important because our project, for example, in Turkey, is about old buildings. It's not about new buildings. They will take care almost automatically through new legislation, but the overall problem is with existing buildings. So this will be difficult to do because, like, for example, the World Green Building Council, it will be impossible to have net zero energy buildings. So we have to rely on nearly zero energy buildings. The buildings can be efficient, they can be really good in taking care of people, but we have to rely on renewable sources, on making the difference between on-site and off-site consumption to get a grip on the emission targets and achieve all the agreements that are there for the global emission reductions. For this, we have to make sure that we understand what causes the consumption in buildings, starting by our own buildings. So the commercial buildings, and not mentioning the residential buildings, which are a different concept. We know that in commercial buildings, the HVAC, so the heating, ventilation, and air conditioning represents around 45% of the consumption of energy, and lights around 17%. Other like plug loads, for example, represents about a little bit over a third of the energy consumption. We know that commercial buildings are 40% more energy intensive than residential, and we know that, for example, the European Union average, 30% of the consumption is gas, natural gas, and 32% is electricity. So we have a good idea of where to start when we think about reduction of consumption. So it's all about climatization, ventilation, and lightning loads. So they are the most easier also to take care, because it's really difficult to tell an hospital, for example, to take out all the medical equipments from the energy plug. So these other 36% charge that is here, it's difficult to take care, and it's really money consuming to take care. So we have to search for also the economical rationale for implement all this. So we know that are things that we can do that are much more easier to do. For example, it's easier to take care about management and operation. It's almost a no value or no money measure. It's easier to take small measures instead of big measures that are really expensive to do. And we have to search for going electrical, for example, to have more efficient equipment, more renewables, and take care of building management systems. So to have everything that takes energy from a building to be really smart managed, to have this effect. So the idea is take care of what is cheaper and easier to do, and keep an eye always on the economical side of all this, because as we will see this in detail a little bit further in the presentation, but it's okay to talk about energy reduction and and net zero and so on, but we have to make sure that everything that we do here, and that if everything that we try the market and the people to do, there's always mandatory economical rationale, because if not, you are always doing laws, designing ideas, but no one is able to make them work in real terms and in practical terms. So it's really important to know what the market can do efficiently. The near zero examples, if you look in any Google search or something, you will always start by the great Northern European condominiums and small buildings that were designed or refurbished as nZEB in the near past. So these are two examples, one from Austria, one from Munich. There's a lot of examples. If you search, you'll get, I don't know, a zillion of examples. Almost all of them are in the north of Europe, and almost all of them are residential or small buildings. So it's difficult with the idea of having a really low energy need in a building. It's really difficult to get the big old buildings, the hospitals, the big universities, the big courtrooms. It's difficult to have them put in the same category as these beautiful examples that we are seeing in these two pictures. You see a lot of green, a lot of very good insulation. They are always in the north of Europe because it's easier to manage, because there's a lot of heating and not much of a cooling need during the year. So it's easier to get a really low energy need for the buildings. But right now, we are getting to another level of energy building, using another reference, not the really low energy consumption, but using the comparison between energy certification schemes. Like you see these two examples from my country. You have an old courthouse, it's not that big, but it's an old building, and you have an hospital, which is really similar to the Turkish hospitals that I saw in our audits, and I saw when I was in Turkey. But it's a new concept, it's a new kind of reference, and it's a new idea about net zero. This connects with the idea that I was trying to explain in the first slides of this presentation, which is what the definition of the net zero buildings that we are talking about. So depending on the difference, depending on the reference that you are using, you can get these beautiful, small, residential, Northern European buildings, or you can get Southern European, Portugal, Turkey, Spain, Italy, old hospitals. These two can be two different sides from an nZEB idea. So as a summary of this first part, I would like to state and to try for you to understand that nZEB is a liquid definition, so it will evolve. It already evolved since 10 years ago, and it will change. The energy in buildings, it's mainly right now a developed world problem, but it will be a worldwide problem. Net zero buildings, whichever definition are we talking about, they will help a lot keeping this problem at bay, keeping the consumption low. And with different definitions, we will get different interpretations of the rule. So it's important that you, after this presentation in the near future, when you speak about and talk about and think about net zero, near zero buildings, you understand that all depends on what we are talking about. We can have different interpretations, very different definitions, which may imply different techniques and different ideas about all this. So let us focus a little bit more in what is the approach in the European Union, but starting with the world net zero definition. So this is a table. Sorry for being a table, but it's difficult to translate this information in another way. My friends from our joint venture was always telling me, please make it visual, please make it colorful, because people will sleep after a little bit. But please bear with me. This is just for you to understand the different interpretations of these concepts around the world. So we have here a couple of examples from Australia, from the United States, from Asian countries, Japan and Korea, and from some references that are used all over the world. So we have a couple of requirements, of metrics that each country or each system defines as useful to tell if a building can be a net zero or a near zero or not. So firstly, we have the metric analysis. What we are looking for, it's primary energy, final energy, or just carbon emissions. As you can see, normally we are used to talk about primary energy. So it's the input, it's from where the energy comes that is important here, and not so much how and when it's used in the buildings. Carbon emissions is used Australia, United Kingdom, but it's not widely used. So there's a relation, as you know, between carbon emissions and primary energy, but sometimes using the carbon emission makes it a little bit more clear about reductions of emissions and not of energy consumption. So it's two different approaches. Another issue is if we include or not the plug loads. So plug loads, it's everything that is connected to the electrical or energy grid, but it's not part of the building pure energy consumption. Mainly, as you can see, the plug loads are included in a lot of countries, United States, and in the Green Building Council, for example, norm, but they are not included in the APBD in the European Union and in Asian countries. We will see why that happens, but it's an important disclosure to do. Normally, all the values are calculated, so it's difficult to use measurements, real world measurements, to make the net zero understanding of the reality of the building. And then it's the renewable use. We already talked a little bit about this. So if the renewables is on-site or off-site, and even inside these two categories, the on-site and the off-site, there's a lot of differences. We'll talk especially about this a little bit later on. And how are the requirements taken care? So it's a share, it's a percentage, it's an absolute value. So we see that almost every country, almost every system has a hardwired system for value for the minimum requirements for this. This chart tells you that there's a lot of different assumptions. There's a lot of different approaches of this thing, but we can see one thing. So we are always talking about primary energy, final energy. We have to take care about the plug loads to tell how they behave on these. Do we calculate or measure? How is the role of renewables? And how are the minimum required expressed? We see that on average, the countries and the systems, they talk about primary energy. They don't take care of plug loads. They are out of the equation. All the values are calculated. They are not measured. The renewables normally are on site, and there are always values for the minimum requirements. We can say that these are the 5 guidelines, main guidelines for analyzing this issue here. It's important to see that all the different concepts, all the different interpretations, they always rely on these issues for telling someone that the building is a nZEB building or it's not a nZEB building. So let us focus, like I said before, in European Union. I focus in European Union because, well, it's probably the most complete, the most advanced system around the nZEB idea. So there's a lot of directives from the European Union, a lot of laws that all the countries are obliged to make, and it's a fairly good system that could be a good example for this presentation, and could be a good example for, I don't know, the future Turkish legislation regarding this. So there are four main sentences, four main ideas for this, which can relate to three, but we must start by saying, like you see in this table, so the idea of net zero is to reduce the current requirements. So the energy use must go down. And from the future energy use, the low energy use, some part of it is from fossil origin, so it's gas or fuel or wherever, but the other part must be renewable. So this chart is the most important chart of all these. So energy use must go down, energy supply must have a strong renewable source. And we can see this in the four sentences. So we should have a very high energy performance in a building, a very low amount of energy required, a numerical indicator of primary energy, and a very significant contribution of renewable energy for the remaining energy use that we cannot decrease by changing the requirements or changing the system or changing the current energy use. Let's go in detail through this definition. So firstly, a very high energy performance of the building. This is really tricky because it could have several different definitions, and even us in conversation we can come up with several different concepts regarding this. But the idea is that the current requirements have to go down for existing buildings, for example, and the nZEB threshold for energy consumption must be lower, significantly lower than the one that we are used to see. And the energy use of a high performance building has to be really low, while trying to keep up the indoor comfort conditions. So we see that a lot in Portugal, for example. I think that Turkey has the same problem. We see a lot of buildings that don't consume energy because they don't have heating, cooling, or proper lighting systems. So that's not the idea. The idea here is, while to have heating, cooling, and good lighting systems, to have a really low energy use. So this is the idea, this is the concept that is behind this short sentence that is written in the European directive. Again, the second one is a very low amount of energy required by the building. So we now are in the building needs and not in the energy supply. We are in the energy use. So it has to be low. The final energy has to be low. And the energy required should be this final energy. The idea of this sentence is to separate what is consumed in the building from what is supplied to the building. So we don't want to have buildings that have a high energy consumption, but all of the consumption is renewable. So the building, the load of the building has to require a low amount of energy, good insulation, good fenestration, very efficient systems. So the building has to require low energy. We have to put a number on this. That's the message of the third idea. So we talk about energy supply, energy intake of the building. We should put a number. try always to put a number on this to know what is low consumption. So here they say that should be a numerical indicator of primary energy in kilowatt hour per year per square meter. The idea here is to know the fossil, the non-renewable energy supply that comes through the building. So what is the maximum that we are supposed to take when we are talking about a net zero? So we should have a zero right here. If you're talking about net zero, we should have a near zero, so a low value is needed for this, but should have a numerical indicator. This is the most difficult thing to do. And if you see in all over the Europe, there's a small amount of countries that could have done this with reliable numbers. We talk about this a little bit further in the presentation also, but it's not easy to set up these values. And finally, we should have a very significant contribution of renewable energy to cover the remaining energy use. So take note of the remaining energy use. So the remaining energy use is the one that we cannot take out of the building through energy efficiency measures or through envelope measures. But we have to make sure that from the energy use, the small energy use that the building has, a significant amount is from renewable sources, which is, well, we can talk about if it's on-site energy generation or if it's off-site energy generation, and we can say, well, we can discuss what is significant. It's 25%, it's 50%, it's all of it. So that is open for discussion. And as we can see in a moment, there's a lot of different opinions in Europe regarding this. But the point is, we have to make it renewable. These indirectly will have a role in the measures and in the style of audits that we are going to perform in a building for having nZEB. Because we only can make renewable what is, well, electrical in a sense. So the electrification of all the consumption is a goal in all this. So we have to take out the fuel, we have to take out the gas, we have to make it more friendly. So we have to make it almost electrical or biomass or something, but we have to make sure that all the energy use that we do, it's possible to have a renewable source behind that supply. So, time for a short quiz. 3 main nZEB rules. We talk about them already, so I don't know if you can tell them, but we are talking about very high performance building. We are talking about very low amount of energy, and we are talking about significant renewable energies. These are the 3 main topics of the net zero rules that are important for this conversation. Everything can change, but these 3 ideas have to be in place to know if this is a viable net zero building, near zero building, or it's not a building that is performance. This is a impossible to understand chart, but this is the different approach for every European Union country that there is. Well, the UK is still here, but the UK is not European Union anymore. So this is a chart that defines what are the different approaches to a lot of net zero characteristics that are here. You can see that there's always probably there's not a country with the same approach in the European Union regarding this. So sometimes there's not a detailed definition. I remember that these plans should be approved since 2018, so it's 4 years ago, but we know that sometimes there are a lot of countries that don't have these definitions in place right now. We don't know how is defined the very high energy performance. Some countries have final energy approaches, other countries have primary energy approaches, and other countries, like the case of Portugal, for example, or France, they say that if you have the top building class in the energy certification system, you are a net zero. This is the approach that I talked about before, to have an old hospital to be an nZEB. So that hospital is an nZEB right now because the refurbishing that was done last year made it in the top building class for existing buildings. So they say that with this characteristic, it's a nZEB according with the Portuguese legislation. And there's a lot of different definitions of amount of energy required. Sometimes there's a limit on the U value of the insulation. Another, there's a limit of lightning power or efficiencies of the HVAC systems or the heating or cooling total energy demand. So there's a lot of interpretation, but as we can see here, normally there's a requirement, a limit on primary energy. If you can see, there's a lot of countries with these requirements, but they have also a lot of other requirements. And the most difficult thing to do is to set up the share of renewable energy, and especially if the energy is on-site or off-site. In these subjects, everything, each country is all over the place. So there's definition almost for every idea and for every opinion regarding this. There's a country that says that the on-site is equal to the same grid. So if you are pulling renewable energy from the Turkish grid, you are doing an on-site renewable energy. So there's a lot of differences between countries regarding the approach that each one follows regarding this. And like I said, there's a lot of places that don't have any definition on place. So what I'm trying to say here is that Turkey trying to have an nZEB pilot test for this project and having already set up some studies regarding this, it's not behind schedule or in a low completion of these goals regarding the European Union. So we are all on the same stage regarding this issue. Everyone is trying to know what should be done and how it should be done to make it a proper idea. In the European Union, with this, there's always an economic problem. There's always a fight, a war between what the Brussels and the European Union sets as a general rule, and now a poor country like Portugal, for example, will spend trying to make the idea viable, because it's very different for Germany, for example, to make this happen, or Turkey or Portugal, because there's not enough money in the economy to make everything according with the letter of law. So we have to make sure that we are not trying to ask for impossible rules. There are two methods for setting up the net zero, the near zero idea. Firstly, using a reference. That's the way that Portugal follow, and France as follow, saying that if you have an A or an A plus in your energy certificate, this is good. So it's good for in this chart. So it has to be good. So it's near zero. It's not net zero, but it's near zero because compared with our normal building, it's very good. And we have the second approach, which is using absolute values. So the building with some preset specific consumption is considered near zero. In the ideal world, we would say that if a building has a zero net consumption, should be a near zero building. So we have to make sure if we understand what the absolute value is, but the idea is having these two main frames to sort out the near zero, net zero approach. The point here is using one or the other, all the indicators should be aligned with the cost optimal framework. I will have a slide explaining what is the cost optimal, but the idea is using a reference or using an absolute value, we have to make sure that we are on the economical good side of all this. It's no use to ask for zero value when to achieve zero, you have to spend $1 zillion changing a building or building a new building because it's not going to happen. So the cost optimal has to be in place at every idea of this. So the reference, like I said, so for example, an A class, it's considered near zero. It's okay, it's perfect, understandable. You can change the A class for the A plus class, for example. There are some pros with this method. The impact of the climate zone is taken care, and the building type is taken care. So we have to agree that the classes of the buildings, they change according with the building type. So an A class is different in an hospital, or is different in a school or a residential place. So this is taken care. But we have to make sure that a very strong reference is needed, and the calculation of the reference is also important. It's not easy to calculate, right? Because you have always to make all the calculations for setting up the energy class of the building, which is sometimes, depending on the countries, depending on the systems, is not easy to do or easy to calculate. The near zero cannot be zero or even near zero, because, for example, an A class in Portugal or in Turkey, it's about the same. It does not translate to near zero consumption, which sometimes is difficult to explain to someone that does not understand these issues, that a near zero building does not equals to zero consumption building. And this can be achievable without renewables. So it depends on the definition and the method that is followed for the A class or the A plus class or whatever, but theoretically can be achievable without renewables, which we saw that it's not a very good thing to think about this. And the absolute value. The absolute value is really simple. So you say that, well, a building that has 55 or 45 or 65 or wherever watt per square meter of primary energy intake, it's a near zero building. So it's very easy to calculate. So you make a measurement or make a dynamical simulation or look at the invoices or something, and you already know if it's near zero or not. But there's the influence of the climate region, and the influence of building type is not there. So the only way for this to be taken into account is to have references, different references for different climate zones, and different references for different use type of buildings. The renewables can be on-site or off-site, so this has to be complemented with something else. And why 55 and not 30? Why 30 and not 178? That's the role of the cost optimal analysis, which is difficult, time-consuming to do. But the idea here is to have, or we may have, these two different ideas, these two different concepts. This is an example from Portugal. This is fairly complicated. Sorry about that. My colleague Serkan had a lot of conversation before he understands this, because this is our legislation. For us, it's really easy to understand, but it's a system that is not proper. Well, it's not the Turkish system, so it's difficult to say. This is a fairly example of a certain way of doing this analysis based on energy certification. We only have two things that we must take care. First, the building has to be better than the reference building, and we have a class A for this. So take notice that in our system we have the A plus energy class, but for our near zero building we say that the minimum is the A class. So for us it's not even the best class available, it's the second best class available. Let me try to explain this a little bit better. It's not exactly like this, but the idea is this. So you have to be better than the reference. The reference for new buildings in Portugal is class B, without any renewable contribution. And with the renewables, this has to be much better than the reference. So twice as better as a reference has to be a class A. For example, if you have, the building is this one, so it's a little bit of half, more than half full of a bottle, a baby formula bottle. The reference, it's half of this. So my building has to be class B. So my actual building has to come down by 25% to be on the reference. And finally, for achieving the near zero energy building certification, you have to decrease by 25% the reference value. So our our near zero, it's not zero, can have a huge consumption, but what we are trying to say is that our net zero is better than the reference and is much better than the actual state of the building. So we know that on this we are decreasing the overall consumption by 50% roughly. Sorry, not the consumption, the energy intake. So we are reducing the energy consumption by 25%, the final energy consumption of the building, and we are reducing the intake by another 25%. This is a fairly easy approach for near zero buildings. Keep this in mind. This is an achievable definition. We are not telling the economy to make impossible things, but we have to explain people that the near zero, it could be not so near zero. This, to be well done, this has to be done accordingly with the cost optimal approach. This is in all definitions of the European Community rules, and it's really important to have this always in the mind, because when you will try to have a proper nZEB legislation, you have to spend a lot of time doing this. Why 55 and not 30? So the cost optimal it's a fairly easy concept to explain. So we are having this energy consumption in the building, And we know that to reduce energy consumption, we have to increase the cost of installations. We know that, right? So we know that if we want to take care of low energy buildings, we have to spend money in insulation. We have to spend money in new windows. We have to spend money in new systems. But there's always a place, a sweet spot for this, when my investment equals the least energy that I have. Because afterwards, I'm going to spend a lot to decrease my consumption, and after I'm going to spend also to have a lot of energy consumption. So there's this sweet spot where everything has to be set around, and if you do this properly, you will tell for each type of building and for each building location if we are talking about 55 or we're talking about 30, because we are going to simulate, we are going to create a reference building. So we are going to say, for example, small office buildings, big office buildings, small hospitals, big hospitals. So you can have a matrix of 30, 40, 50 buildings. We are going to change the technologies in this reference building and see what is the best NPV, so the net present value of investment versus energy consumption for the time life of the building. And we use the best NPV for the best technology. If we do this for in a sample big enough that can have, for example, different HVAC systems, different pumping systems, different ventilation systems versus different insulation systems, different fenestration systems in the same building, we will get a value. We will get a number to see if we are asking for 55 or 30. Just to give you an example of the difficulty of doing this, one of the Portuguese universities with an energy government lab, they did this for a small office building in Lisbon, and they just changed around the load of the building, which was insulation, and the climatization, the cooling system that they would use in the building. They sort out a matrix of 96,000 values, just changing insulation versus cooling system. But after this calculation, they would know that the least consumption that a small office building in Lisbon could take was 65 kilowatt hour per square meter per year. And that was set up the reference building for that kind of building that they would later on write in the Portuguese legislation of the nZEB buildings. So it's a very difficult thing to do, and it's a very time consuming, but it's a very transversal analysis that everyone has to do to know what should be the reference value that one uses for this. I talked about this. There's a difference between reality and perception that we have to make sure that we understand. In this project too, when we finish the pilot, I think for sure a politician will say that now we have a building that has zero energy use, zero invoice of electricity, which is not real, right? So in reality, we have always a consumption of the building, and the net zero is always not near zero. So there's always something going on with the fossil consumption, which is difficult to get rid of. But the perception will be this is a zero consumption building. we have to make sure that we all understand what we are talking about when we talk about zero energy buildings. And finally, the story of off-site, on-site. It's really important for this. So we know that we have the energy use, the final energy use of the building. Then nZEB requirement is lower than the actual requirement. But we know that we can have, theoretically, we can have the on-site renewables and off-site renewables. We can have zero primary consumption in a building. It's not that difficult. I don't know, I think you have this also in Turkey. You can sign for a green electricity supply from one of your normal suppliers. You have guarantee that the energy that the grid supplies to you is green energy. We can say that this green energy is off-site renewable. So it's not difficult to do, and it's not difficult to understand. So it's not difficult to have a zero primary energy consumption using off-site renewables. And there's a lot of different ways to get this done. So on-site renewables, you can have a roof photovoltaic system. It's normal to have. I think in Turkey, I saw a lot of photovoltaics in the roofs. So you can generate that in your premises, in your building. The off-site renewable right now has a lot of options. It's not only the options that were available a couple of years ago, but right now you can have a PPA. So you can have a purchase power agreement with someone that sells photovoltaic energy from one site that is not near your building. You can have batteries, and you can have even wind power purchase agreement. And you can, with this, have one thing that was impossible a couple of years ago. It was to make sure that you have renewable energy during the whole day. So you can have off-site renewable during the nighttime, you can have off-site renewable during daytime, and you can have, with the batteries, you can have, you can rely on the peak power consumption to be also on renewables. So it's really important right now to have this idea well explained of off-site, on-site, because you can have a fully loaded building just running on renewable energy right now. It's not difficult, it's not that expensive, and it's a good way to think. So in each of the definition that we use, we have to make sure that we understand what we are talking about when we say, well, it's an on-site or off-site. For example, the Portuguese legislation, they took care of this. They say it's on-site, right? You have to be connected to your building, not on grid, but you have to have the power cable has to go inside your building for this. So the summary of this second part, and before we have a quick break for having some coffee after your lunch and before mine. So the idea of near zero, it's clear, but there's a lot of different interpretations. No country uses in the same way. So Turkey can have a different legislation from what we are talking about here. There are two trends, reference value versus absolute value. And it's important to keep an eye on public perception. It's important that people, the normal, regular people, understands that we may not be talk about of zero energy consumption buildings. We talk about good buildings regarding energy consumption. So if you have some question, please just shout, I will be here. If not, we'll see you in 5-10 minutes for our second part, which is more practical and more related with our KBEV projects. So see you soon.
Thank you, Miguel. How much time do you need to?
5 minutes, for example. Depends on you also. What you think it's okay. For me, 5 minutes is okay.
Okay.
Just to grab a cup of coffee. Yeah.
We can start at 2:40 p.m.
Okay. Okay. Perfect. Perfect.
Thank you.
Everyone is alive?
Okay. I think they are.
Okay, let's hope so.
Okay, we can continue.
Okay, so we in the first part we talked a little bit about the concept of all this, which is really important. I've been in a couple of conferences where people present nZEB buildings and they say how they calculate things and they say, well, this is a really good building and so on. And they present architectural draws and system draws of the whole thing. But in the end, we are always talking about that building. We are not talking about the system or the concept or the idea of all this. So we thought it would be important to understand the idea, because when you are familiar with the idea and the concept, you can easily interpret new situations and new possibilities that can arise. And if it's important because we are talking with people from the government, engineers that will in the future talk about this, and it's much more easier to rely on the overall concept than with a particular detail of that building, which can change over time. So that's why we spend so much time doing this first approach. So let's move with our project. So in our KBEV project, we have pilots for nZEB. So as you know, we are going to do audits and we are going to do construction works in many buildings, but some of them will be made for demonstration of this net zero concept. So remember that in this, because they will be demonstration projects, it will be really important the perception of a near zero building that we talked about before the short break. So we have to make sure that we can explain this. So the idea was that the buildings could include deeper renovation and newer technology that is not common in Turkey regarding buildings. So passive house building ideas, waste heat recovery, cool and green roofs, and so on. So this was the first idea, but we have to make sure that we do this with economical rationale, because if not, the demonstration value will be demonstration value for one architect or one ministry, but not demonstration value for the market, which is the overall objective of this. In our operation manual, there was a definition of nZEB for this, and it was absolute value reference. We already talked about this, so the idea was, it's 4 ideas mainly, which took all the right notes regarding the definitions that we saw before. So it was set up a numerical value for net primary energy, numerical value for primary energy and renewables, and overall savings from the building, which implies that the building has to be in the future a high performance building. And finally, the class was an A class, the best class in the system for the best building in the system. So this is pretty much okay, pretty much perfect as a definition. We see this kind of definition in a lot of countries, for example, Denmark, Germany, Poland, Italy, in a bit, as some kind of definition is very similar to this one. And the ministry already did studies regarding nZEB definitions. So I think you will probably know this. We had it translated to English to understand everything that is written there. So, but well, they took or you took different building end uses, educational, offices, healthcare, and residential. They put the buildings in each of the 4 climate zones and Turkey, and they use it with the software that they normally use for the energy performance certification in Turkey. So, and they come up with a sort of optimal cost analysis, and it's fairly informative, and it's fairly fair work that can be the basis for the future work that has to be done in a different way or in a more deep way to have these calculations for the cost optimal done. So they did this, and what they say in the end of the document: net zero definition, near zero definition cannot be determined on a fixed energy consumption value because of regional climate differences, building functions, and different demands originating from different indoor thermal comfort equipment. So if we do a fixed energy consumption, a number for this, we have to make sure that we have all the climate zones represented, all the building functions represented, and different demands, different efficiencies from different systems that are on the building. See that this relates with a couple of things that we discussed already. So plug loads, absolute values, reference values. So it's you see the importance of having a strong definition of net zero buildings to have all the things really sorted out. This is an example of how this definition works in the real world buildings. So these are 12 buildings, 12 compounds, because there's a couple of buildings inside each of these hospitals and schools that we did the detailed audits that this team did back in 2019. You'll have here all the real values, the real calculated and measured values from our audits. So we have here savings of primary energy. We have the renewable energy production, we have the new primary energy, and we have the new primary energy without the renewable production. We see that it's impossible to have a near zero building using the small absolute values that we have in these hospitals, for example. They save a lot. The measures that we forecasted, that we studied, they save a lot. To have 25 to 50% of savings, it's a lot of work to be done. Sorry, it's a lot of work to be done. To have renewable energy of 30 kilowatt hour per square meter, it's a lot of energy to be produced. But even so, we only can achieve 340 or 500 or 200 kilowatt hour of primary energy. So this is a sign that, well, the building type has to be in this definition, because if not, it would be impossible. For example, we only could achieve the nZEB definition in 3 schools. And they have fairly low consumption, because schools are special beast on these analyses, because they don't consume energy in summertime. They are closed. They are closed for summer. They don't consume energy, in nighttime, for example. So they don't have that much heating load during the other part of the year. So it's a fairly specific characteristics that make this nZEB concept. So the investment will always be large. So we have a couple of scenarios in these audits, and the scenario used was always a deep one, so it's always the expensive one. There's an issue with the renewable production. So if we assume that we have to have a large part of the energy profile being done by renewable sources, it's difficult to do in large buildings and in high consumption buildings, the hospitals, for example. So it's difficult to find space in an hospital to have the kind of photovoltaic production, for example, that we need for these issues. So we have to make sure that we can adapt the definition to the system and to the reality of things that we have. So regarding the definition that we have in our operation manual, there are things that have to be improved. So another things that are really good. So the 50% energy savings, it's very good. So we have to make sure that we save, right? When we have a refurbishing of an actual existing building to make it near zero, we have to save. It should be a large saving percentage. 50% it's perfect. Could be higher though. The class, the A class, it's coherent, right? Because it's the best class. So we have to make sure that we have the best class for the best building. There are things that, well, we have to make sure. So up to 45 kilowatt hour of renewable energy means that if the building consumption is low, we can have zero energy, renewable energy, which at the same time can comply with the norm, with the definition, but it's not the idea. The idea is always to have some renewable source here, and we have things that we have to change. So there's no rationale for the 55 kilowatt hour or 100 kilowatt hour or wherever. We have to make sure that we have the building location and building use accounted for, because if not, it will be impossible to do. And we have to set up some sort of economical rationale for the operation, because if not, it will be impossible to do. We are going to just spend money, and it's difficult for this to be implemented in the real world, even if it's the World Bank paying or if it's the government paying, because someone has to take charge of the first bill, of the first invoice of all this. So we propose to use in our project, in our pilots, to use a reference-based approach. The EPC, the performance class, cannot be used as a sole reference because our Turkish system is not flexible for this. So the software that you use, the way that you use the architecture types, it's not very good for doing this. There's not enough systems, HVAC systems, for example. So we are very, it's a very closed definition, very closed system to use. We don't have cost optimal studies for setting values. So I told you, right, it's a lot of time. These studies have to be done, but they are not done yet. So we cannot rely for these pilot projects for cost optimal. We don't have also a large pool of detailed audits. If we have 1,000 detailed audits of 1,000 different end types, use types, we could say that on average, a very good building has X consumption, but we don't have that pool. And from the pool that we have well, dozens of audits already done, we have a lot of buildings that have an artificial low consumption. Like I already told you, it's a school without heating, or an hospital without proper lighting systems. So we have to make sure that the references that we use, they use comfort levels. They provide comfort levels to the people that are there, because if not, they don't suit this. In Portugal, when we launched this program, the first definitions, I was in the government back in 2013, and we had a problem because the energy savings of hospitals, for example, was going and take out one of 2 lamps, right? If you had 10 lamps in the hallway, you took 5, and that was the idea of energy efficiency. Well, it's not the same, right? Because it's an energy efficiency because you don't provide comfort, or in this case, good lighting levels. So we have to make sure that we use the proper things. So we have to define a reference, but accordingly with the building behavior. So we propose 5 requirements for this. So energy savings has to be big. So we put here 60%. So you have to from the original building to the new building, we have to make sure that we save a lot. The class has to be A class. We keep this from the definition. It has to be a good building. We say that up to 50% of final gross primary energy has to be made of renewables. We say that primary energy consumption has to be made against a reference calculation. And we say that the improved building has to be better, 60%, for example, better than the reference building. We will compare the real with our improved reference building. And the cost of all this, of the bundle of the measures, have to be less than X years. 30 years, for example, 20 years, it's up for discussion. How we are going to do this using the reference building? This is the basis of the energy certification in France and Portugal and Spain, for example. We have one building model, and we will create 3 different inputs for the building model. 3 inputs which relates with the reference, which is our reference building. The actual building, it's our baseline, it's our real world building. And the improved building, which is the future building, when we implement all the measures that we anticipate and we calculated for having a high performance building in the future. So there's a couple of things that are equal in the 3 inputs. So the building architecture, the occupation profile, and the plug loads are the same. So these will make sure that we are always analyzing the same building. It's the same hospital in Istanbul, is the same school in Ankara. So we are always using the same school with the same people in there, with the same plug loads. We are, like you see, we are taking the plug loads from the analysis of a net zero building or near zero building. We say with this, we take out, for example, all the incredible loads that an hospital has in medical equipment. We put the hospital at the same side of a school, for example. So building architecture will be the same, occupation profiles are the same, and the plug loads are the same, which is not the same. The things that manage the comfort levels and the load of the building are not the same. So the insulation values of the envelope, the opaque envelope and the windows are different. The HVAC systems are different. The hot water production is different, and the lighting loads, the lighting systems are different too. So we are going to use reference values for our reference. So we are going to say, what is the normal building? You already have this for example, the U values of the walls. Your regulation already says what is the normal, what is the basis of the system. We are just saying that we are going to increase those references to HVAC systems, to hot water production and lights. For the actual input, we will use the real values that we discovered in the audit work. So the real U value of the envelope, the real coefficient of performance of the HVAC, the real light loads, we are going to use that for our actual. And for the improved model, we will do like all the audits, right? We are going to use what we proposed to change from the real model to the improved model. We'll change insulation, we'll change the chilled water production, we will put some renewables, wherever. But we are going to use these, but using always the same building architecture and the same occupation profile and plug loads. What reference values to use? We have a couple of examples. This reference idea is not, well, we didn't come up with this for ourselves. The APBD uses these normally in several countries. So I told you about Portugal, Spain, France, a couple of others use this reference. So for the values, the EPBD, the European Union system, they specify different values depending on climate zone and type, but well, from 0.4 to 0.7 watt per square meter Kelvin. HVAC systems, we are going to use, they assume that the COP or the RRR are 3, for example. And we assume that the reference system is there if nothing else is installed. I will come up this in the next slide. For example, we specify that the normal reference boiler has an efficiency of 95%, for example. And we assume that the lights have a DPI of 2 to 4 watt per square meter per lux. So there's a couple of different approaches to this. This European Union uses these values, but for example, ASHRAE norm 90.1 defines another approach using the same idea, but defines another approach for each of these 6 categories of references. And for example, EDGE, which is another system which is paid by the World Bank, uses another set of references. But as you can see, there's a fairly common approach for this. What do we propose to use here? Okay, for the envelope, for the insulation, walls and ceilings and floors and windows and so on, we propose to use, well, the Turkish building code. So our reference is this one. Even if the building could be lower than this, but the reference has to be this one. So our near zero building has to be measured against this reference. It's not very good, it's not very bad, it's a reference. For the HVAC systems, we are going to say that the COP is 3, and we are going to assume that the reference is there, even if in the real model, nothing is installed. What this means? This means that if the building as a low artificial consumption, real consumption, because they don't have cooling or heating, we know that our reference would have cooling or heating. So the baseline will be higher in the reference building than in the real building. And because we are comparing our near zero building, our nZEB building with a reference, we don't care if in the real world you don't have the air conditioning installed or connected. Because in our reference, you will always have an air conditioning system. The same for ventilation and the same for water system. So we specify with a table, we specify how much ventilation the building should have. For example, you cannot have a school without fresh air intake. Normally, you get that intake by opening the windows, right? But in our reference building, we are going to say that each student has to get 30, I call it, meters of fresh air, cubic meters per hour, cubic meters per hour per student, for example. And the same thing for the lighting system. So we are going to say that normally with in the ASHRAE, they have a table for this. For libraries or for medical offices, you should have 22 watt per square meter of lights if you have an efficient system. So this will be our reference building. This will be agnostic for the overall country. You can have the same building in Izmir, in Ankara, in Istanbul, because we are going to compare the building with the same building. We are not going to compare the building with something that is not there. This will help a lot on having a strong system putting in place. We are going to say also that the overall payback time will be less than 30 years, for example. We are jogging with this. Some people say 20 years could be okay. I, for example, say that 40 years could be more useful. But the idea is to have this economical benefit for the overall building package, which will make sure that some measures that are really good, really easy to pay for example, lights are always a good example, which has a really short payback, can be on the same accounting than, for example, insulation, which is always difficult to have a good payback time. So in the overall balance, in the overall bundle of all the measures, we can get, like in this example, 17 years, which is perfectly reasonable for this. It will be our reference for economical value of the overall thing, because we don't have enough cost optimal studies for saying that this is perfect or not. At least like this, we know that this makes economical sense. So it's the bundle 17 years, it's okay, it's less than 30, so let's go with this. We will study a little bit, we'll jog a little bit with the cost optimal, like you did in the ministry publication that we spoke about a couple of slides ago. So we are going to check with all else unchanged, we are going to check in key areas, mainly insulation, what could be useful. For example, if our real U value is 1.5, it's a really crappy building. Our reference value is 0.7 from our legislation. We will do the following study. We will see how the building behaves with a 0.2, a 0.5, and a 0.7, which is a reference U value. And for each of these, we are going to measure how many savings will be in kilowatt hour, how this relates for the economical savings, financial savings, how this will have as a construction cost, how will these will have as an operation maintenance cost, and finally, with all this data, what is the best NPV value for this? It's fairly easy to understand that sometimes, and this is the concept of optimal value, the best value is not the 0.2, because the incremental value in kilowatt hour savings, it's not enough to make room for the unbelievable cost of this solution. So we are going to, in real terms, normally go for the average solution, which gets a fairly good energy savings and doesn't cost that much. We can always do kind of a multivariable scenario like we did, like I told you, in Portugal with the 96,000 combinations. We can always make sure that we change the U value, and then we change, for example, the heating boiler to see what is the best combination NPV for this. It's a kind of a matrix analysis, which is more time consuming, but we could do this in particular pilot projects to check out what could be implied. This is the approach that the government will have to follow if they want to make a good cost optimal approach. So it's this multiplied by zillion. But the idea is this one. So how we are going to calculate this? So it's easy to explain, not difficult to do, but easy to explain. So we'll create a model building. So we'll use the architecture, the plug loads, and the occupancy profile of the real building. We will put all these in a dynamical simulation software. Sorry, but we have to use a dynamical simulation software with this. We cannot use the simplified model that, for example, your software for energy classification of buildings uses. We have to use Sequest app. We have to use Energy Plus or something that has the simulation computational power to check out all this. So we will create a reference, architecture, occupancy, plug loads, to know the actual situation. We will propose the measures to achieve the nZEB, the percentage savings and so on, including the payback caps that we did. We will check afterwards the insulation or something else for the cost optimal scenarios, and we choose the final scenario and simulate against the reference building. The percentage of the difference will show the final nZEB status. So remember that with this model in place, it's fairly easy to change the inputs and to simulate what happens if you use the real world building inputs, or use a reference building, or use the improved building. The key here is to build the model. I don't know if some of you are used to use dynamic simulation software, but it's after a little bit of learning curve. It's not difficult to do, and it's a very powerful system to check all these differences. But the basis is this: create a model, use the inputs of reference, real and improved, and see what happens. The audits are different for doing this. It's a good question, good point, right? Because we want to make the audits that we are going to do for this project, for example, but in the future, we want to keep the audits as much as the same as possible as a normal audit. It's different because we are going to use dynamical simulation. I know that some of the audits that are already being done and were done in the past for this project use dynamical simulation software. So it's not a big thing. We have to set up different conditions for the reference building. Well, that is a new thing, right? Because you don't normally use reference buildings, but we have to make sure that we say of that important categories of building insulation, building equipment, we have to make sure that we set up the good reference. We use real consumption info to calibrate the model. Sorry about this mistake, to calibrate the model. So we have to make sure that the real consumption values are used for making sure that the model is well done. It's fairly standard for dynamic simulation. It's not difficult to do. It's not a big deal to do. The conditions, of course, for meeting the nZEB requirements are new, right? We have to make sure that it's 55 or 60% of savings, class A or something, but we know that these numbers are calculated anyway in any audit that engineer makes. So we are not asking for something different than the normal work that we do in an audit. Calculate primary energy, final energy. We do that all the time. So the audit is the same. It's not different because the field work is the same. So the measurements that we do is the same because we have to make sure that the improved and the real calculation is there. The consumption analysis is the same, right? We have to know how much consumption goes for lighting systems, for HVAC. We have to know that. The proposed measures are equally the same. So we are not searching for something different that normally audits propose, maybe a little bit more measures, more deep measures, but the kind of measures are the same. So as a summary of this, we build up from previous work to come up with a reference value. This reference has to be location and then use agnostic. And for this project, we propose a method which is based in simulation software of a building reference to compare with the actual building and to compare with the future building. Let's take an example of all this, how to turn a normal building into an nZEB building. Let's go for example based. It's not the same because the situation is different, but based in the vocational and technical high school in Bursa. So it's a fairly common school. It was made in 1980, so it's around 40 years of service. It's 13,000 square meters of floor area in 5 blocks. We want to make sure that you all understand what kind of calculations are we going to do. This is based only in measured data, not calculated data. And we have some premises for the example. So we have to assume that the building can maintain the required comfort levels, which is not particularly right in this case. The reference building method that we proposed would not change the results. So we didn't do the reference building method for this particular example, but the end results could be the same. And we assume that the measures that we will discuss in a few moments will achieve an A class. So we didn't make this calculation too, but well, it's not fairly complicated to assume that we are talking about an A class building after all this. So the school is like this. So it's a fairly common school. Could be in Portugal too. We have a lot of schools with this setup. So you see in the image in the left, you see the 1, 2, 3, 4, 5 and a half pavilions of the school. So it's a fairly simple building. So a lot of fenestration here, some air conditioning, as you can see here. And the energy consumption that we check out in our audit are these ones. So we have a total consumption energy of 1.7 million kilowatt hour of primary energy. So relating with the indicators that we used, we say that this consumption is around 130 kilowatt hour per square meter of office space. So you get a feeling of the profile of this school, right? It's electricity and natural gas. That they use a lot of natural gas for heating purposes, and electricity mainly for lights and plug loads. In this, it's a fairly common building in Turkey and Portugal too. So what we proposed for energy saving measures? Well, we say that we are going to put a new insulation and new windows in all of the building. So the building did not meet the heat insulation standards. So we are going to change that. We are going to save a lot of natural gas because we decrease the load of the building. This is an objective of the nZEB structure. So we decrease the load, the required load of the building. We also change the boiler for a heat pump. So we take care of the rest of the natural gas consumption. We increase, unfortunately, the electricity consumption because the heat pump, well, consumes electricity. We reduced the light consumption by putting LEDs in everything, in every lighting fixtures, and we added a PV photovoltaic generation facility in the buildings. We see that there's a lot of roof to put PV in this location. So this is a fairly normal situation. With this, we completely wiped out the natural gas consumption, so 100% of savings. And we decrease a little bit of the electricity consumption of the building. So we have the payback period of all this, it's 10 years. Well, it was not 10 years, but for the purpose of this example, it's 10 years, which is below the 30 years that we specified as the maximum of this. So it's a perfect example for an acceptable economical value for these refurbishing measures. So what will be the end results of this? So before we have 130 kilowatt hour. After we have 60 kilowatt hour. So we reduced around 68% of 68% of the base consumption of the building. We add up almost 20 kilowatt per square meter of energy production on premises. So we have the final primary energy consumption of this building is around 41 kilowatt per square meter. Sorry, this is wrong. These numbers are wrong, but well, these are right. So you'll see that this building, using these kind of references, you'll get a nZEB status. So we have an A class, we have production, we have a much more efficient building, we have a decrease in the primary energy consumption. So as you can see with this fairly normal example, we show that it is not impossible to get a nZEB building with these rules. Of course, building location and building type helps. This is a fairly easy climate zone. It's not in the deep heating south or in the deep cooling north, so it's fairly easy. We see that we don't have occupation when the cooling loads are bigger. So it's summertime, the school is closed, so it's fairly good to have this kind of profile, especially because the school didn't have a cooling system. So in this sense, the reference building and the real building are perfectly matched with this, with the real needs. The building has a low insulation, so it was easy to improve. We'll see here. So this is the real building before the measures were put in place. So as you can see, it's a fairly low, it's a fairly, well, not good building. So putting some rock wool in these, the U values, they go down a lot. So it's good because all the loads of the building are very connected with the insulation load. So it's fairly easy to take care. So right, you take out of you move the insulation, and the load comes down almost instantly. And as you can see, the electrification, it's a fairly good way to reduce the energy supply and to make sure that the renewables are there. Because, you know, it's much more easier to put renewables in the electrical consumption. So it's a fairly common ground to go to change the gas, for example, for electrical, even if you decrease the primary energy intake because of fuel switching or energy efficiency measures or whatever, but it's fairly easy then to have a renewable part on this. So it's three examples that makes I wanted to make sure that we all understand the building type and location really helps of having these. Insulation, low insulation helps also because it's fairly easy to go up. And electrification, it's a fairly good way to go, and it will be a solution that you'll see in the future, not just in the building sector, but also in the transportation sector or industry sector. Electrification, it's the way to go. If you take out hydrogen, electrical power, it's the way to go because it's fairly easy to treat. So typical measures, like I told you, they are not much more different than the measures that we normally talk about. Insulation, in this case, insulation, change the boiler for an heat pump, LEDs, and PV generation. You can also easily, and we have examples for these, using condensing boilers, for example, a little bit more efficient. So changing the motors and putting variable frequency drives in all the electrical plugs, making sure that we have good building management systems in place, changing for biomass boilers. It's not easy to do in every territory, but that hospital that I talked to you about, the A class of the hospital was because they changed the boilers for biomass boilers. They have emissions, but they have zero primary energy. So it's a fairly good solution. Of course, ground source heat pumps, when it's available, it's a very good way to go. Or cogeneration, having solar thermal hot water production, and having cool chillers, for example, with variable frequency compressors for some more cooling power solution. The objective is always reducing the loads and improve the efficiency of HVAC and hot water production. So as you can see, it's not different from the normal audit. Maybe here we have to go a little bit further in the reduction that we are trying to get to make sure that we come up with a really low consumption, high performance building. Summary of the last part, we are almost finishing. Renovations can also achieve the nZEB status. It's not difficult, it's not impossible, it's not easy, but it's doable. Building type and building use are really important, and there are some typical measures that can be used for this. So thank you for this. These 2-hour sessions over Zoom or Teams are not easy to do. I guess that it's not easy to listen to. Our project will take 1 year more, so we'll have time, I think, for in-person to get over this again. We have a lot of work to be done yet in the nZEB department in this project. So I think that this is the first conversation, not the last conversation regarding this. If you have questions, please, we are on the, well, it's almost time. It's now time for wrapping up the 2-hour session. If you have any questions, please go ahead. If I don't know the answer or it requires more time, please give to Enes and to Serkan the email that we go back for a more personalized answer when we can. So thank you for your time. And I'm available for whatever you decide, please.
Thank you very much, Miguel. Yes, as Miguel said, if you have any questions, you can ask here or anytime by mail. I think no questions. Okay, thank you for your participation. Miguel, thank you for your presentation.
Thank you very much, Miguel.
Thank you.
Sorry, I couldn't participate in the beginning because we had a meeting with the general director. But unfortunately, because of the workload, I cannot participate in the meetings lively. But later, I am really checking and watching the videos.
Perfect.
Training videos. Thank you very much.
Perfect. Thank you. Goodbye, all. Serkan.
Miguel, for your time and for the detailed presentation. It's been a lot of data, a lot of information.
Sorry.
And but you have enriched it with concrete examples, which is really good. I think that gave a broader idea and more concrete idea about what we are talking about when nZEB is mentioned. That at least cleared our heads in terms of definition and the concepts. Esra Hanım, en azından bayılmadan bitirdik yani bir tane daha eğitimi. Bir sıkıntı, sağlık problemi çıkmadan. Herkese sabrı ve zaman için teşekkür ediyoruz.
Az kendi personelinin de bizden paralar
Görüşmek
Okay,
üzere.
bye-bye. See you soon.
See you.
Bye-bye.
Bye bye.
Bye-bye.